again. Let's go back to the spreadsheet again, looking in your book at exercises 10.13 and 14. So if you want to report the equation of the regression line for this sample from a bigger population, you can use these numbers. You can report it as y hat equals, the slope is about 0.9468. That gets multiplied by x, and then the intercept is about 21.499. Remember that x is the assessed value, and y is the sales price. You can then use this equation to make predictions about what a typical house of a given assessed value x would sell for. What do you think the person who's trying to sell it would sell it for? You plug into this equation. What else does the problem ask you to do? And we're going to go over it into section 10.14, exercise 10.14 as well. Sticking with 10.13, it does say obtain a plot of the residuals. Is there anything unusual? Okay, we already got the summary output and we included it with the residuals right there. And it should have included a plot there. Yep, here we go, there's the residuals. So this would be a plot of the residuals, which you can make by doing what I did, using the Excel minor analysis tool pack, getting the summary output, and making sure you check the residuals and residuals plot boxes, and you can get this plot. The question says, is there anything unusual to report? Do the residuals appear approximately normal? What you're looking for is you're looking for basically random scatter of the residuals about the horizontal line at 0. And you're also looking for spread in the y values, the residual values, that's approximately the same for each value of x. I don't see anything real extreme here. Basically, they do seem random, both above and below the horizontal line at 0. Are there outlier residuals? Well, yeah, I guess that one might be kind of an outlier residual, though it's more an outlier for x, the assessed value, than it is for y, or y minus y hat, the residual value. It's more of an outlier for x. It's a bigger house, a more expensive house in terms of the assessed value. So I guess I wouldn't say that's really an outlier, other than just saying it's a higher priced house overall. This one has a fairly high residual. Y minus y hat is fairly big. So the sales price y is a lot bigger than the predicted value from the regression line, y hat. But it's not too terribly out far outside the range. I suppose if you ignore that outlier and perhaps this one, in a sense these maybe typically have a little more negative residuals than positive residuals, but the effect is not too strong. I would say the assumptions of random scatter and normality for each value of x are definitely not too far from on the mark. If you saw something like this in the residuals, some sort of pattern that was not a random scatter, or if you saw something like this, maybe lots of high values here and then lots of negative values over there, or something like that, that would not fit the normal pattern in the regression model. But again, here we have random scatter, and again, the amount of scatter in terms of the absolute value of the residuals is basically the same for each value of x, so it's not too far from the normal model on that real informal assessment. So based on these answers, looking at part F, do the assumptions for linear regression analysis appear reasonable? I would say yes. Okay, for those exact same reasons. There's basically random scatter. For each x, there's random scatter in the y's, and the amount of scatter in terms of the variability in the y's is approximately the same for each value of x. Not exactly, but approximately. Moving on to 10.14, now we actually do some calculations. You can certainly use Excel to do the calculations. We've got the equation of the regression line here based on the slope and intercept here. You have different new homes that are coming on the market, say, for different assessed values. One that's 155,000, one that's 220,000, and one that is 285,000. If it wasn't clear, these numbers were in thousands. make this bigger at the same time, not losing where I am. Okay, so these are 3 new houses, say, on the market for these 3 new assessed values. What would you predict for the sales price that the homeowners are going to ask for? These are like asking prices, sales prices. Use the regression equation. Use these coefficients. Maybe you want to use more decimal places and round at the end. You can do it with a formula. Here you can do equals $G $39. That's where the slope is. Times X. That's in the cell J42 here. Plus the intercept, which is in cell G38, use dollar signs, so that we can copy and paste. We get these predicted values. Okay, so that would answer part A. Part B, you calculate the residual. I'll let you do that part. Again, what do we have here? These are X values, these are Y hat values. I guess these must be data points though, actually, aren't they? Oh, it's for different numbers, sorry. Part B is different numbers, different X values, that are actual houses that are on the market right now, not these houses. Okay? So you do something similar for part B in calculating Y hats for actual houses that are on the market. You could go back up to the actual table and find those and do the calculation up here. One of them, for example, is the house with the sales price of $142.9 thousand. Where is that? That's the assessed value, excuse me. I don't see it. Another point of confusion. Oh, okay, sorry about that. I'm misreading the problem. Suppose these new houses that I was looking at already, sorry about that. So these are X's here. Those are X values, these are Y hat values. Then in part B they tell you the actual sales prices. 142.9 thousand, 224,000, 286,000. These still are the new houses that are not in the original data set. Calculate the residuals, do Y minus Y hat for each of those. Construct a 95% confidence interval for both the slope and the intercept. I guess the assumption is based on the data we already have, not based on this new 3 data points. Really, in assigning that problem, I was trusting that you knew how to get this Excel output here, which was part of what I did poorly in assigning what I assigned here for today. We already have those confidence intervals right there. So all you have to do for this part is just look at those intervals. Your 95% confidence interval for the intercept is about -9.8 to +52.8. Your 95% confidence interval for the slope is right here, about 0.78 to 1.11. There are the answers. In part D, they ask you to assess, based on one of those answers at least, whether there's evidence, maybe both of them, whether there's evidence that this estimated regression line differs from the diagonal line y equals x that I drew earlier. Remember that? I made the scatter plot. I drew the line y equals x, which would be the line where the assessed value and the sales value were the same. Do we have evidence that our population regression line that we didn't actually ever plot because we had a sample, do we have evidence that our population regression line differs from that? Remember, these are intervals that are supposed to estimate population parameters. We have sample statistics. This is B0, this is B1. What are those numbers and these intervals for? They are for estimating population parameters beta 0 and beta 1. Since this interval contains 0, we do not have strong evidence that beta 0 is not 0. It could be 0. And since this interval contains 1, we do not have strong evidence. I'm not going to put a p-value on it. We do not have strong evidence that beta 1 is different from 1. In other words, putting these two intervals together, we do not have strong evidence that the population regression line is not y equals x. Based on these sample data, if we give the null hypothesis the benefit of the doubt, say that beta 0 is 0 and beta 1 is 1, intuitively, without putting a p-value on it, based on the fact that this interval contains 0 and this interval contains 1, we do not have strong evidence against the assumption that the population regression line actually is y equals x, that the, on average, so to speak, the sales price does not differ from the assessed value. That's what that part is all about. We do have strong evidence against the null hypothesis that the population slope is 0. That's not asked for in the problem, but we do have strong evidence against that null hypothesis. And this p-value, which is so close to 0 that Excel rounded it to 0, it didn't even put it in scientific notation. It technically would be an itty-bitty positive number that's so small you could hardly even imagine it. That p-value is so close to 0 that it rounded it to 0. We have definitely really strong evidence against this null hypothesis. We would definitely reject this null hypothesis. This interval does not contain 0. If you wanted to calculate it by doing a calculation and using a table, you'd use these numbers. That's the standard error for B1 without the formula. You know, I quizzed you on the formula. This is the corresponding t-stat that can be calculated with this formula that I showed you at the end of class last time. The t-stat is that ratio B1 over the standard error for B1, really B1 minus 0, because the null value of beta 1 is 0, divided by the standard error. It has the same form that Z and T always have. The value we got for x bar, or for p hat, or in this case for B1 minus the null value divided by the corresponding standard error. Same pattern. You don't need to bother putting the minus 0 in there because it doesn't affect it. And in the book's formula, they don't bother putting it in there. But this ratio, taking this number, the 0.9468, and dividing it by this number, the 0.0806, gives you about 11.74. Try it on your calculator right now. You should know that. You should know, you should be able to check the numbers on this table to that extent. Take the 0.94, I'll go ahead and round some, 0.9468 divided by 0.0806, and we should get about 11.74. Well, we won't get exactly what we see on the screen there because of rounding, but pretty close. 11.75. Okay, I want to round, I want to use more decimal places of accuracy if I wanted to round it more precisely to 2 places after the decimal. So you should know that. What's the degrees of freedom here? What was n? N is the number of observations, that's 30. Happens to be right there. Degrees of freedom would be 20 what? If n is 30? df here would be 29? No, 28, n minus 2. So if you were going to use the table in the back of the book, you'd have to go to 28 degrees of freedom. I won't show it on the screen. For 28 degrees of freedom, the t-stat we got above 11 is off the chart. Okay, the biggest number on the 28 degrees of freedom line is 3.674. 11 point whatever it was, where I lost it here, is way off the chart. The p-value is much smaller than the smallest p-value in this chart. You could say it's definitely less than the smallest p-value in this chart. And again, Excel rounded it to 0 because it was so small. Okay, so we would definitely reject that null hypothesis. What that kind of says is the regression's worth doing. There is a linear relationship between x and y that has a non-zero slope. This regression is worthwhile to do. It's kind of the point of that test that we just did. We just did a test, you know that, right? There's the null and alternative hypothesis. The p-value we saw was essentially 0. We reject the null. We've got strong evidence that beta 1's non-zero. This is past these exercises, by the way. And we would reject that null hypothesis. The regression's worth doing. We have a linear relationship. We have at least evidence that the linear relationship, if there is one, it's got a non-zero slope, which makes the regression line equation worth using. Take a breath. We're going to do something new now. Kind of need to see these things 2 or 3 times sometimes, Haley.
What's the significance of the p-value for the intercept then?
It would test whether the intercept is 0 or not,
Yeah.
but that's not typically something we worry about, and I don't think you have any exercises on that. Something new. Like Mac puts these things in different spots than the PC does. There we go. 2 new kinds of intervals come up in section 10.2. In that section, when the book discusses it, it's pretty much just looking at computer output without looking at formulas. We, however, are going to look at both computer output and formulas, though for this next assignment, you're just going to look at computer output. Confidence intervals for the mean response of y given x. I probably should have added up there. Given a specific value, x equals x star. This x star confuses people. It's not in any table. Okay? In our books, stars are used to denote special numbers. Z star, T star, here, X star. The X is star denoted as a special number. It's a special number that we happen to be thinking about. What number is it in general? It could be anything. It depends on the situation. We've got a regression problem. We pick a certain value of x that we'd like to know information about the corresponding y's for that value of x. We call that value of x x star. You are typically told what x star is. There's a problem. So they might not label it with an x star. It's the value of x you're thinking about. We plug that number into the sample regression line, find y hat, and then we find what's called the confidence interval to estimate the mean of the y's for that given x, I should add. Or x equals x star. Based on n minus 2 degrees of freedom, takes this form where this standard error is a new kind of standard error, and it's got a formula we've never seen before, and it's a very complicated formula, right there. What we want to understand for today is not the complicated formula so much. We'll do that next Tuesday. We want to understand the purpose of this interval. And probably it's best explained by looking at the book's examples. We're going old-fashioned here. I've got some transparencies. We're going to look at the book's examples of what's going on here. When I do transparencies, it's easy to get them mixed up, though, and they stick together. There we go. That's right. Turn this thing off. So here's a page in the book, and we're going to focus on an example in the book. I will rewrite the formula in its abstract form here as well. Y hat plus or minus T star times the standard error from mu hat. Maybe zoom in on that so people who are watching on the video can read it. Okay, what's the big picture example here? This is about relating job stress and what's called LOC, locus of control. It should be vaguely familiar if you've been doing your reading. You've got a locus of control is supposedly some psychological measure that measures how much control somebody feels like they have over their lives. Do they feel like they've got a lot of control over their lives or not? It's a little unintuitive, but the book phrases it as saying low LOC, low locus of control, actually means you've got a lot of control over your life, or you think you have a lot of control over your life. Whereas high LOC corresponds to having a low amount of control over your life. You feel like your life is basically ruled by randomness. Low LOC means you got a lot of control. You feel like you have a lot of control. High LOC means you feel like you don't have much control. Stress is another psychological measure. You know, it's an opinion, basically. How stressed do you feel? When you put numbers on these things, it's a little bit shaky because it's not real precise. You know, how stressed do I feel? Level 1, 2, 3, 4, or 5. It's not a real precise thing you can really measure. It's a feeling. But psychologists and other social scientists try to put numbers on these things anyway. So you got data about a bunch of people. I think it was 100 people. I think N was 100 here, if I recall correctly. That was your sample size. Relating LOC and stress. LOC was horizontal. That was the explanatory variable X. Stress level was Y. How does stress respond to LOC, the locus of control? And they made a scatter plot and calculated a regression line. It had a positive slope, indicating higher LOCs, where you have less control, you feel like you have less control, corresponding to higher stress. And lower LOCs, where you felt like you had more control, corresponding to lower stress, which makes intuitive sense. Statistical software is used in this example to give you some output based on people who have an LOC of 16. What would you predict their stress level is the idea. The 16 then is the X star. Okay, because that is the particular LOC you're thinking about. You're wondering about all people who have locus of control values of 16, whatever that means. Don't worry about what it means. I don't know what it means exactly either. Okay? You don't have to know. What is their stress level? The output is right here. This is Minitab output, which we don't use, but you should be able to read it in the way that I'm about to describe. The number right there that's labeled with fit, that is the Y hat value when X equals X star. In this case, that's 16. Sorry that I wrote 2 stars. I think I was trying to write an X, but it started to be a star, and that's not erasing. I thought I have an erasable mark. All right. This standard div fit is the standard error for mu hat. It's this thing. That is SE mu hat. So the output is giving us that. And then this confidence interval here in interval notation is the confidence interval for the answer. Could you figure out the plus or minus notation based on that? Yes, you should be able to. Y hat, 2.894, there is the midpoint of this interval. So to figure out the margin of error, you just need to take, say, the right endpoint and subtract Y hat. The margin of error here would be 3.0374 minus Y hat minus 2.894, whatever that is. I won't bother calculating. That would be the margin of error. Could you figure out this SE mu hat if you were not given it based on this interval? Yes, you could, because you could figure out T star. and I believe it was 100. You look up 99 degrees of freedom, which I think is actually not in the book, so you could maybe round it to 100. Playing it safe rounds it down to 90, but 100 would be closer to the t-star value that would be in the book. The margin of error equals t-star times the standard error, so you could figure out the standard error if you had to. But what's the purpose of this interval? That's the more important thing. The purpose is to estimate the population mean. For all those people whose LOC value is 16, what are the mean of the Y values? That's what this interval is meant to estimate with 95% confidence. For all those people whose LOC is 16, we estimate with 95% confidence that the mean stress level is between 2.7507 and 3.0374. Okay? So that's one thing you can read. There's another new thing here. It's got something called a 95% PI. What's a PI? PI stands for what's called a prediction interval. I've got it on the PowerPoint, but for the sake of time, I'm not going to go back up to the PowerPoint. Let me just write down the general formula for a prediction interval in this context. It has a very similar form. It's still y hat plus or minus the margin of error. And the margin of error is still a t-star times the standard error. But it's not the standard error for mu hat. It's labeled in our book the standard error for y hat. We never talked about prediction intervals before. It's a new thing. There is a formula for this standard error for y hat. That's in the book and on the PowerPoint. I'm not going to show it to you. It's pretty similar to the standard error for mu hat. Just one slight difference that actually can make a big difference calculationally. We won't focus on calculating it today. We'll just focus on understanding the meaning of this. What does it mean? Well, the 95% that goes with this prediction interval still is a level of confidence, even though we don't use the word confidence. That's the first thing to realize. The 95% does reflect a level of confidence. We're calling it a prediction interval instead of a confidence interval. Why? Well, it's not meant to capture a population parameter. This interval, this confidence interval, is meant in a sense to approximate a population parameter, the mean of all the y values for the given x in the population. Say that again. This interval is meant to estimate a population parameter. That parameter would really be the mean of all the y values for a given x value. In this case, x is 16. The mean stress level for those whose LOC is 16. That's meant to estimate a population parameter. This is not meant to estimate a population parameter. Prediction intervals in general are not meant to estimate population parameters. They are instead meant to estimate sort of next observations for y, in this case when x is 16. For those people whose LOC is 16, and you're about to observe somebody new who you haven't observed a value for before, you happen to know their LOC is 16, what do you think their stress level is? You're 95% confident it's between these two numbers, whatever that means. Okay? What does the 95% reflect? It's kind of hard to describe here. You know, you've got sample data, you got a sample regression line, you know, these calculations are based on a sample. If you resampled over and over and over again, either by simulation or by theory or by actually doing it, which would be a real big pain, so nobody really ever does it that way. If you resampled over and over again and recalculated this interval over and over and over again for x equals 16 over and over and over again, the idea is about 95% of those intervals would capture the next observation for y when x is 16. Weird. Okay? I'll say it again next time, but that's what it means. Hang with me for just another minute or two here. Don't start putting stuff away. It can be distracting to me and to others around you. To finish off here, class, you should also strive to understand these graphs. that are in the next couple pages. What do we see here? We see the scatter plot for LOC and stress. We see the regression line in the middle there. We see two dashed curves. What do those curves represent? Those are representing, if you think vertically, a bunch of different confidence intervals for different values of x. A bunch of different confidence intervals to predict the mean of y for different values of x. For x equals 16, for example, the confidence interval goes like that. To the left here. The lower bound and upper bound of the confidence interval to predict the mean of y for that given value of x is this interval right there in this graph. You could do it for other values of x. Like over here at x equals 5, you could do that. At x equals, say, 13, you could go about like that. Notice that it's skinnier in the middle, closer to x bar. X bar is somewhere in here. You've got better intervals in a sense when you've got more data, closer to x bar. Finally, look at this picture. This picture shows a similar thing except with prediction intervals instead of confidence intervals. Those dashed lines look like straight lines, but they're actually curves, but it's not as extreme as the other picture. For each value of x, like x equals 16, this gives you a prediction interval for that value of x. And do notice that most of the observations for the sample are between the two dashed lines. And we'll talk more about this next Tuesday. See you guys.